In this video, we'll be verifying for network reduction using star delta transformation. We'll see theoretical calculations, some basic concepts, and how do we solve this on a hardware. I'm Professor Mohan BS, working as assistant professor in Department of EEE SJBIT. So to verify the given network using star delta transformation over hardware, that is discrete, let's revise the concepts of star delta and delta to star. So here the blue colors are in star delta and the black are in delta. So star, as you can see, they are known as YT and 4-wire system. So the given are, these are the four ends. So the given are star elements, the center one are called as neutral, and these are delta respectively, known as mesh, delta, pi, or 3-wire system. The three ends are A, B and C. Neutral does not exist in delta. So let's see here delta to star transformation system. So that is the known are in delta, the blue color, the unknowns are in Y, that is black color. So as discussed, these are delta which are known, RAB, RCA, RBC. One we have to find is RA, RB, RC. Based on derivation, we have seen that RA is equal to RCA plus RAB divided by RA plus RBC plus RCA. So RA is in contact with RAB and RCA. Thus, the way to analyze is product of those two divided by sum of all the elements. Similarly, RB, it is in contact with RAB and RBC, which are known. So RAB known element and RBC are the known elements. So product of those two divided by sum of all the element will give us RB. Similarly, for RC, which is between RCA and RBC, I repeat, RCA and RBC are the known variables. RC is what we are trying to find, that is we are converting delta to star. So product of RBC and RCA divided by all will give us 2 star elements. So that's what you have seen is delta to star. So here, based on the derivation, we know the formula for star to delta. That means now the knowns are star, RA, RB, RC. We have to find the delta elements. This RAB, RCBC and RCA. So the formula is based derivation for RBC. So between RB and C. So which two star are connected? RB and RC. So those two products, and the one which is not connected would be in its denominator. So RB into RC which are connected divided by the one which is not connected, and then summation of those two elements which are connected. So that's how we can generalize for the conversion from star to delta. Now similarly, if we want to find RAB, so RAB is in contact with RA and RB. So sum of these two and their product, but which is not in contact or which is perpendicular to RAB, which appears perpendicular, that is RC. So product of those two divided by RC plus RA and RB would be the equation for RAB. As you can see here, product would be RA into RB divided by and their summation, and the denominator for the product will have RC, which is actually not in contact with RAB. That's how you can memorize or understand from the derivation, that is after derivation. Similarly, RCA, you can pause the video and write the equation. RCA is RA into RC divided by RB plus RA plus RC would be for RCA. So now in the given experiment, they say to calculate and verify the unknown resistance and total current if voltage of some voltage is applied across it using star delta or delta to star transformation, and also justify by Ohm's law. So let us solve this by two methods. So the first method, let us see. So this is the given circuit. So step 1, let us remove the circuit with the voltage source and ammeter which I have actually given in the circuit. Let us assume the values. So after the values are known, where do we start? Should we directly apply star delta or should we apply delta to star? No, always first analyze if there are any circuits, elements which are in series and parallel. Then apply either star to delta. If they are not, then apply star to delta or delta to star transformation. So let's see here which all are connected in star and which are connected in delta. So star as Y of 4 wire, delta or 3-wire system. So these three are connected in delta. These three are also connected in delta, right? So you can see R3 is in common between the two delta elements. Thus, remember this, we cannot apply simultaneously for these two delta meshes. That is, we cannot convert delta to star simultaneously for these two loops or meshes because R3 is in common. Now, how does this appear? This appears in star. How does this appear? This also appears in terms of star. How does this appear? This also appears in terms of star. Thus, we have two delta elements and three star elements. And where do we start? Right? So, as I told, first analyze if there are series and parallel. If you can pause the video for the answer. If there are any elements in series or parallel, you can analyze. Later on, you can unpause the video for the answer. I hope you have guessed it correctly. There are none of the elements are in series, none are in parallel as of now. Okay, so we have to apply either delta to star or star to delta. So the first method, let us see, we will apply star to delta. So here we have assumed the values. The same values will be there in your lab, in a discrete labs. So let us calculate the same. So we'll apply this star. We know that there are three stars. You can choose any one. So I'm choosing this as first method. So converting this star to delta, where are the three? Where the star has 4 ends, right? So, but for converting star to delta, we'll take only 3 ends. So this is first end RA. So equation for RA. What are the equation for RA? Which two are connected? 330 into 330 divided by the one which is not connected, 470. Plus sum of these two will give us 891.70. Similarly for RB, which two are connected? 730 and 330. So their product divided by the one which is not connected, 330. Plus this 330 plus this 470 would give us 1270. Similarly RC, right? So now what we have done, we have just identified where we are applying. We analyze that none are in series and parallel, and then we have just started by applying star to delta. We've selected one out of 3 stars. We've just selected 1 star, applied star to delta. So once we have converted the known star to the known delta, remove all those star elements. So please observe, all the delta elements are removed. Sorry, all the star elements are removed and retaining the delta elements respectively. Right? RA was this value, RB and RC was 1270 ohms. Now, where do we start? Should we again apply delta to star or star to delta? No. Here again start from scratch. That is, analyze any are in series or parallel. If they are not, then only apply star to delta or delta to star. So here, pause the video and analyze if any elements are in series or parallel. I hope you have analyzed it correctly. So we have these two elements which appears in parallel, right? So we know equations for parallel. So 891.70 into 330 divided by their sum, right? So that will give us 4240.862. Similarly 1270 and 470 are in parallel and will give us the answer as 343.045 ohms. Now, so this step has been completed. So this is a reduced circuit. Then now what do we do? Again analyze for series and parallel. Any element in series or parallel? Now you can see that these two are in series, right? So now these two are in series. That's step 4. The answer is sum of these two will give us 583.908. Now what do we do? Again analyze for series and parallel, and this time these two resistance, that is RC and 583.908, appears in parallel. Thus that's step 5, and RA into RB divided by RA plus RC, RA into RB divided by RA plus RB, that is R1 into R2 divided by R1 plus R2, the form that you know for parallel, will give us 400 ohms. I just retain the same value here, or variable of RC, but the value of RC has changed now, as we are aware. And how does these two appear? They appear in series, right? That's step 6. Sum of those two will give us 330 plus 400 will give us 470 ohms. So what we have done here is, if you go back and check, we have analyzed for series parallel, none are there. Then we have chosen out of 3 star, any one star we have chosen and applied star to delta, and from there on we have just analyzed for series parallel only. Okay, so there are problems where you have to multiple times apply star to delta or delta to star, and after that, after probably 1 or 2 steps, you have to analyze only for series and parallel. So let's see method 2. So this is where we started. We applied star to delta. Now what I'll do is I'll take this delta, highlighted delta element, and we convert delta to star. So this delta 330, 470 and 470 are in delta. So these are the 3 ends, correct? So this appears 4, but at the bottom it is together to form one junction or one node. Connecting together forms neutral, and you have R1, R2. Randomly, I'm assuming R1, R2, R3. You can arbitrarily choose any one, as this one as R1, this one as R3. You can choose. So what is the formula for R1? Pause the video, write down the equations and the answers also for R1, R2, R3. Then you can unpause the video to check your answers. I hope you have unpaused, got the right answers. So equation for R1. R1 is your star deriving from, or the equations are from delta to star. So the known delta to unknown stars, right? So unknown star R1 is sum of these two, right? These two are in contact. So 470 into 330 divided by 330 plus 470 plus 470 will give us 122.126. Similarly for R2 and R3. Then what do? Remove all the known delta which you've got in terms of star, retain star, remove the delta element. Remove 330, 470 and 470. Retain these 3 star elements only with their respected values. Okay, so this is very important to retain the values R1, R2 and R3. Do not swap accordingly. Okay, so R1 was 122.126, R2 was 122.126, R3 was 173.937. So retain respectively. Now what do? Step 2, analyze for series parallel. Okay, so series parallel, which all are in series, which all are in parallel. So this 330 and 122.126 are in series. This 330 and 122.126 are in series, right? So you can see once you enter this, when the current enters this, the same current follows through 122 also. Similarly, and another current enters to this 330, the same current enters to this 122.126 ohms, and they meet here, and both the currents flows through this, right? So in that way we can say the currents are same. Thus we can say this two branches are parallel, but in this branch these two are in series, in this branch these two are in series, and this is your answer. And as discussed in the few seconds back, these two branches appears in parallel, right? So the answer becomes 226.063. Now all three are in series, and then your answer is 470 ohms. The same thing we have got in method 1. So you can see there are 2 delta and 3 star, so you can apply 5 different methods. I've just shown you 2 methods. So in exam you can arbitrarily choose any method. If the steps are right, at the end you will get the same answer. So how do we connect this practically? So we have springboard, and we have respective resistance R1, R2, R3, R4, R5, R6 respective values. So R1 is placed accordingly according to the circuit diagram. Similarly R2, similarly R3, R4, R5 and R6. So all are placed according to the circuit diagram, and then let us connect them. So before we connect, so what you can see here is actually a voltage source, that is your RPS, regulated DC supply. In our lab we have regulated DC supply up to 0 to 30 volts. The maximum current it can supply is 2 amperes. So 0 to 30 volts and maximum of 2 amperes. So you can see voltage course, and then current, and we have plus sign, positive polarity, and negative sign here of your DC supply. So current has to be set maximum, so that you are demanding for current. So if you do not set the current maximum, it will not allow whatever voltage you set. Okay, and this voltage course is to vary in terms of decimal points. You have to vary very minute variations, then you can use voltage course for fine tuning. So we use this voltage knob to vary the voltage. And this is the DC ammeter, where red indicates positive, black indicates negative. So let's see how do we connect all these. That is your voltage source, ammeter, and resistance. So here, from voltage source to R1, this is from positive voltage source to R1, and then we have from R1 and R2 to R4. So between R1 and R2 to R4, and then we have R4 to R3 and R6. So R4 one junction to a junction of R3 and R6 which are connected together, and then R5 and R6 are connected. R6 and R5, or R5 and R6, they are connected, and then from this junction it's going to positive. So from this junction it goes to positive of ammeter. So from R5 and R6 junction it goes to positive of ammeter, and negative ammeter goes to negative of supply. So negative ammeter goes to negative of supply. So that's how you have to ring up the given circuit. Now, as discussed, set the current maximum, set the voltage. As I told, the maximum voltage you can set is 30, and with slight increase of voltage course it will go up to 32 volts. But the panel says, the nameplate detail says it is 0 to 30 volts. With voltage course, you can increase it up to extra 2 volts. So using voltage course, and the voltage value, let us assume that it is set to 25 volts. And what you have to do is, for 25, measure what is the output current, okay, and using this ratio manually you have to calculate what is V by I. Similarly, set a different voltage, measure the current. I'm just taking randomly a value here. These currents are not according to the resistance that we have designed here. Similarly, set another voltage. So 3 random values of voltage, will get 3 different currents, but the ratios will be approximately same. And how do you calculate average value? As you are aware, sum of all divided by 3 will give you the average resistance by Ohm's law. Right. So this is how we have verified, as discussed in your aim, justify by Ohm's law. So that's what you have done here by Ohm's law, right? But how do we do with ohmic meter? So let's see how do we do that with ohmic meter. So this is the circuit in a lab manual, right? So we have a multimeter. So as discussed in earlier classes, this red color indicates positive, common black color indicates negative terminal, and we have this knob, right? So where do you see ohm symbol in this multimeter? Where do you see ohms symbol? So you see here it ranges from 200 ohms to 200 mega ohms, and you can see here it says ohms here. So voltage, ohms, and capacitance. So you have to connect between common and this point. I repeat, between common and this point for voltage, ohms, and capacitance. So this is the connection, and to find voltage, we'll discuss that in upcoming class or slide. Now let us restrict only for ohms. For ohms, you have to rotate this knob according to your value. Now what we have got 730, right? So we have got 730. If you set this to 200, it means that you're finding the resistance value up to 200 ohms. So but we know that our value is 730, so we have to set it to 2k, right? So 730 is within 2k, and 730 is not within 200, right? So I hope you have understood that why we have to set what are these arrows marks leading to. So where we have to set, we will set it to 2 kilo ohms, as our calculated value is 730 ohms. If it was 100, then we would have set it to 200. If it was 10, then we would have set it to 200. If it was 1k, then we will set it to 2k. If it is 300, we will set this knob to 2 kilo ohms here, right? So as shown in the lab manual, one is between V or ohms, and other is common, and the knob direction should be towards the ohms. So how do we connect? As per the diagram, V to point A, and then common to point B. Even if you swap, you get the same value. And here, after I repeat, after making the connections, you can see in this video, once after making the connections, only then we are actually ringing up. We are connecting the multimeter to the circuit. So do not connect the multimeter. I repeat, do not connect the multimeter and do the settings in multimeter. first do the necessary settings with multimeter and then do the connections to the circuit. So by this you'll get your answer, only one value by ohmic meter. Thus we have verified by Ohm's law, the theoretical calculations are verified by ohmic meter, and we have verified by Ohm's law. So always remember, any hardware, the circuit always must be inspected by lab inspector or the faculty during your CIE, regular practice, and SCE for any labs before energizing it. Thank you for watching the video. Please do subscribe to enhance your knowledge and build the learning curve.